Some observed cosmic structures, like massive walls of galaxies, appear so large that they would have taken longer to form than the 13.8 billion year age of the universe allows. Mature early galaxies, recent observations, such as those from the James Webb Space Telescope, have found galaxies at high redshifts that appear unexpectedly mature and massive, challenging the timeline of slow hierarchical growth predicted by the Standard Model. Reliance on dark matter. Rebuttals often highlight that the Big Bang's explanation for structure formation fails without the placeholder of dark matter, which has yet to be directly detected. Other arguments made to oppose the Big Bang theory. Critics and skeptics of the Big Bang theory generally focus on its reliance on unobserved placeholders and its inability to explain the absolute beginning of the universe. While most scientists accept the model as the best explanation for the universe's evolution, major weak points include: 1. Reliance on unseen entities. The Standard Model, lambda-CDM, requires three major components that have never been directly detected in a laboratory. Dark matter, used to explain why galaxies have enough gravity to stay together. Dark energy, a placeholder for whatever is causing the expansion of the universe to accelerate. Cosmic inflation, a theoretical rapid expansion in the first fraction of a second. Skeptics like LPP Fusion argue these are epicycles, extra variables added just to make the theory fit new data. Has been thought of, assumed by astronomers but not proved or observed through their instruments/technology. 2. The origin problem. The theory describes how the universe evolved, but it does not explain how it started. The initial singularity, mathematical models point to a singularity of infinite density at time zero, which many physicists consider a sign that the current laws of physics, general relativity, are simply breaking down and failing to provide a real physical explanation. Causality. Critics often ask what triggered the event or what existed before it, questions the theory currently cannot answer. 3. Theoretical paradoxes. Traditional Big Bang models faced three classic problems that required the invention of inflation to solve. The horizon problem. Why distant parts of the universe have the exact same temperature despite being too far apart to have ever exchanged heat. The flatness problem. The universe's geometry is almost perfectly flat, which requires an incredibly precise, and seemingly unlikely, initial density of matter and energy. The monopole problem. Theories suggest the Big Bang should have produced many magnetic monopoles, magnets with only one pole, but none have ever been found. 4. New observational tensions. Recent data from advanced tools like the James Webb Space Telescope, JWST, have introduced new challenges. The Hubble tension. Different methods of measuring the universe's expansion rate give different results, suggesting our understanding may be incomplete. Mature early galaxies. JWST has spotted massive, well-formed galaxies very close to the beginning of time, which contradicts models of slow, gradual galaxy growth. Lithium discrepancy. The actual amount of lithium observed in the universe is much lower than what Big Bang nucleosynthesis predicts. Other evidence that supports this theory. I could only find one more piece of evidence, which is: dark night sky. Olber's paradox disproves an infinite, eternal universe. Cosmos has a finite age. Night sky should have been filled with stars, so the night sky would be white, but the night sky is black with only small parts of the universe filled with stars, so that means the universe has a finite beginning. A brief explanation of other evidence that disproves this theory. Missing satellite galaxies. According BBT, when a large galaxy is formed, accompanying the large galaxy should be thousands of satellite galaxies. However, what we actually observe is only a few. Where are all the other satellite galaxies that the BBT predicts? Too big to fail problem. BBT predicts that these satellite galaxies should not be too small/faint to see. BBT states they would be big enough for us to observe, thence the assumption that the reason for all those missing satellite galaxies is because they are too small/faint to be detected is not true by their own theory. BBT predicts satellite galaxies would be too big, therefore they would not fail to show up. However, observational evidence concludes they are failing to show up. Cusp core problem. BBT predicts that dark matter surrounding galaxies in the form of a halo should be concentrated like a cusp near the center of the galaxy, but what we observe is that it is more evenly spread out, contradicting the BBT prediction. We see a uniform distribution of matter, whereas the theory predicts it would be more concentrated where the radius is less, that is more concentrated near the center.